Okay, and let's start with the final talk of this afternoon session before the discussion. And I'm happy to introduce Christoph Minz from University of York. And he's going to tell us about algebras and states for quantum fields on causal sets.
Yeah, thank you for the introduction. And thanks also to the organizers to have me here. Actually, well, the research I'm presenting is from the University of York, where I was doing my PhD. Currently, I'm actually in Germany doing my first postdoc. So I'm going to present some quantization method that is actually meant to, or I presented for a finite dimensional setting, but you might also apply it to other settings. And for that, I'm going to start with a motivation and use causal set theory to construct a particular example that I will then elaborate on this method afterwards. So first, we also have in this session a bit of causal set theory. What is a causal set? Those of you who don't know about causal sets, well, it's just mathematically it's just a partial ordered set with the additional property of being locally finite. That means that whenever you take any interval in this partial order, you get a finite set. And diagrammatically, this is quite often drawn as with these Hasse diagrams, where you have essentially time going upwards, like you usually do in space-time diagrams. And the causality is very similar to a space-time. So even a space-time can also be described as a partial order, but it's not locally finite. And here I just take an example. This is a 3-simplex, so this is the simplest causal set you can imagine that embeds, or needs at least dimension 4 of Minkowski space-time to be embedded. Now I want to do a scalar field theory on that as a simple example. So I just take all the vertices and I define a field on that. So for this finite dimensional example, in fact, this is just something that is isomorphic to Rn, where n is the number of points I have. And to get the algebra of classical observables on that first, we take then functionals of these fields. So any functional of that gives us, in the algebraic sense, the algebra of classical observables. And you can equip this additional to the pointwise addition and multiplication for the algebra. You can also equip it with a Poisson bracket. This is so far off-shell, because we haven't imposed any field equations yet. And you can find more in this paper here. Next, we now want to impose the field equations to go actually on-shell. So what you first have to do, you take your field equations that you might know from your favorite spacetime, and you need to discretize it. So, for example, for the scalar field theory, we have the Klein-Gordon field equation that we want to discretize, and this means that we usually take any point and look into its past, and the past is then split up into several sets, and these sets are then used for the discretizations. And there are different approaches to that. But all of them usually boil down to taking several subsets and discretizing this in this way. And then once we have done that, we can actually invert this operator that we get. So essentially, this is just for a finite setting here. It's just a matrix, so we invert this matrix, and this gives us the retarded Green operator. And then with this, we can also construct the advanced Green operator and the Pauli-Jordan operator. And that will then be essentially the operator that is necessary to get any solution. When we take the image of this operator, this is actually the same as the image of the off-shell Poisson bracket that I've shown before, and this gives our solution space. But this so far was only to motivate one example that you could think of. So now to something completely different. Well, actually, it's not that different, because, as I said, you can use that causal setting for the following construction. So far, everything was classical. Now we want to go quantum, and usually a few methods that you could think of to quantize are deformation quantization in the formal way on causal sets. It has also been done in this paper here. You can also do strict deformation quantization, which is a bit more mathematically involved, and there are further many other methods. But what I want to talk about is geometric quantization, and in particular, I will highlight these 3 points that we will need to get a quantum algebra for that. So we will start with this finite dimensional setting. In particular, Now a bit more general, what we have as an input is just a 2n-dimensional vector space, symplectic vector space, so it has a symplectic form, and also it has an inner product. So these are essentially just our ingredients, and we can relate the symplectic form and the inner product together. Then we have this operator. In this setting that we had before for the causal sets, that is actually very closely related to the Pauli-Jordan operator that you've seen, just to get you, give you some idea what these symbols mean. Now I will say what the quantization bundle is. Well, the quantization bundle is we have our phase space, our symplectic phase space, and now we quantize, so we define a Hermitian line bundle on that. And this Hermitian line bundle, of course, has a curvature or connection first, and this connection, the curvature of this connection is then directly connected, directly given by the symplectic form. And in that sense, you can do the same procedure for any Planck constant. So in the following, I will actually consider h bar as rather a mathematical parameter. So you can tune h bar, and in the limit h bar goes to 0, you actually recover the classical case. Now this is only the quantization bundle. Now we want to choose our physical Hilbert space. And this physical Hilbert space is usually taken to be some sub-bundle of this quantization bundle. And one way to choose that is, as we will do, we choose a sub-bundle by looking at the spectrum of the so-called Bochner Laplacian. So this is a Laplacian which you can define with this connection from the quantization bundle, and this is in that form. And then we just look at the spectrum of that. And if you look at the spectrum of that, in particular for this finite dimensional setting, what you get some spectrum that looks a bit like that. Well, this is just for 2 dimensions, but if you can also increase the number of dimensions. And what you might notice here is that you have one lowest eigenvalue. So this spectrum is actually also all positive, and you have some eigenvalue down here, and then you have a spectral gap. And in more general settings, so whenever you didn't start with a finite dimensional setting, but or with more an interacting field theory, because so far I've been talking about free scalar field theory. So you might also do this for interacting field theory. Then what you would get is, instead of a symplectic vector space, you would get a symplectic manifold. But you can there has been some paper about this, where you could also make an argument about some bounds on the spectrum, so that you can also isolate some lower part. And we take this lower part of the spectrum to define our physical Hilbert space. We isolate that, and then take all the sections of this line bundle that correspond to the eigenvalues or the spectral part here. And explicitly, I've written down some formulas here, but maybe they're not that important. So these formulas are essentially what you would get for the finite dimensional setting. You get just some. You can choose some complex coordinates on your phase space, and then what you will get is holomorphic sections on that. Now to the last step of this. So now we have our chosen Hilbert space, and now we can just define our projector, so a projector to this Hilbert space, and we can use this in a so-called Toeplitz quantization to map from our classical algebra that we have constructed before, or we had given before as functionals. We can now map to, well, if you take Schwarz functions here only, then we map to compact operators. But this can actually also be extended to bounded operators on the Hilbert space. But the fact why I take Schwarz functions here is because now I have my quantum algebra that I get here as the image of this map. But I actually want to also construct states on that. So this is actually the other very important thing in algebraic quantum field theory. You want to have states. So I define myself a measure that is essentially then been used in the next step to define the dual operation to this quantization. So we have seen this Toeplitz quantization, which is essentially starting from our classical algebra here, that I've represented with this disk here, and we map it into some quantum algebra, and you can imagine multiple quantum algebras with different parameters h bar. And then mapping back we can use this measure, which is implicitly defined through this trace, to define a dequantization map. Well, now this dequantization map gives us again a classical observable corresponding to some quantum operator, and we can now use this dequantization map to actually define a state. So in the algebraic sense, what is a state? Well, a state is a functional that takes in any observable, any quantum observable, and spits out a complex number. It has to be positive and normalized. And if you do this with this dequantization map that corresponds or is dual to the Toeplitz quantization map for this finite dimensional setting, in particular for the causal set setting, then what you will find is actually the Sorkin-Johnson state. So it turns out that the state you can define with dequantizing and then evaluating at the 0 point of your symplectic manifold. Yeah. Is then giving you this state, and this is the Sorkin-Johnson state that had been known in causal set theory before, but essentially what we did in this project was find a mathematical way to define the state. So so usually when you look into the literature about the Sorkin-Johnson state, then you usually find some sort of 3 axioms that are imposed on an operator that essentially gives you a 2-point function, and that is then this 2-point function that corresponds to this state, what we have derived here in a more mathematical way. It was also interesting that this state has actually been suggested to also be to be used to do quantum field theories on curved spacetimes. However, if you do that, then you have to be careful because the state is not Hadamard. But there are modifications that reinstate this Hadamard property, and there are also similar generalizations actually to Dirac fermions. And with this, I will actually come to my last slide. And on this last slide, I give you a summary. But so I summarize the steps again that have been taken so far. But I also again want to motivate that this can be also used to generalize the entire procedure to interacting field theories. So in the case of interacting field theories, you would start with again with a Poisson bracket, and you can actually use the free Poisson bracket of your free field theory and modify it with Möller maps, as also been mentioned in this paper here. And then you can follow the same steps of the procedure that I've been talking about. So you can take again the image of the solution space, and then you can define a symplectic space. In the case of the interacting field theory, of course, this symplectic space is now a symplectic manifold. So it's a bit more complicated, but we can still use this spectral condition what we have seen to single out the physical Hilbert space. And with this, we can then use the Buchner. This is what the Buchner Laplacian is used for, and then we can go to this physical Hilbert space and can use the projector to that to define our quantum algebra. And if we can find a dual, so this measure which I've showed on a slide before, then you can find a dequantization map, and with this you can again define the state in a similar fashion. But that is something that we haven't finished yet, so we are actually thinking about this extension to interacting field theories. And with this, I thank you for your attention, and I'm here for questions.
Yeah, thank you for this nice talk on causal sets and matter. Are there questions for Christoph? Philip?
Yeah, thanks for the nice talk. So I'm not sure if it's terribly relevant for the whole program, but I didn't quite understand, even at the beginning when you were talking about fields, classical fields on your causal sets, where does even the free Poisson bracket come from? Is it that you take some, because it seemed like you were taking some kind of algebraic point of view, or you considering it as like a C-star algebra and then you look at flows in the... So there is the notion of the piles bracket you can define. That is a Poisson bracket. Yeah.
More questions? So maybe I have a brief question. So your construction, does it rely on particular causal sets? So do they have to be manifold-like, or can this be like...
No, so the causal set setting was really just to motivate this construction. But as I said, I mean, the ingredients for this quantization construction are just that you have a finite dimensional, well, in that particular case, a finite dimensional symplectic vector space with this inner product and the symplectic form. But the idea actually is to even do this for any symplectic manifold. Then you would have a Riemannian metric instead of the Riemannian metric instead of the inner product, and you would have still a symplectic form on that. And these three ingredients, or these two ingredients, essentially. You can use to construct this. Yeah.
A quick question before we go on to the discussion session. If that is not the case, let's thank Christoph again. So now we have a bit more than half an hour for the discussion session on observables, so we can open the floor to questions to all the speakers of the session. So does anyone want to start? Yeah, because you had a question before, so...
Hi. Well, this is a question for Philip. Well, perhaps it's a pretty elementary question, but it's a question that I have from a long time. Why when people compute things in general relativity, they usually don't pay too many attention to characterize things in a relational or in a gauge invariant way? For example, in element... Oh. It's working? Yes. Okay. Oh, okay. Thank you. For example, when you calculate something pretty elementary like the deflection of the light by gravitational fields, you don't characterize the angle of deflection in a gauge invariant way. So, and it's very usual in people doing, for example, numerical relativity. They don't pay too many attention to characterize things in a gauge invariant way. So my question is, why?
Yeah, that's a very good question. And classically, indeed, you don't really have to do that. You can just do gauge fixing, and then any of these manifestly gauge invariant approaches, I mean, as long as you do a suitable gauge fixing, that will just agree with what's usually done in textbooks and so on. Once you compute predictions in a suitable gauge, I mean, they're physical. Now the question is, what do we do when we go towards quantum gravity? Then possibly this gauge fixing or choosing suitable coordinates may not be present, and then actually having gauge invariant objects is something that is very useful. So it's, in fact, in some sense, more useful for going beyond the classical case. And for conceptual reasons, it's also nice. I mean, there's using this gauge invariant framework, you can also put, for instance, notions such as general covariance in a more physical setting, something I didn't manage to cover. But if you're strictly speaking about predictions, then gauge fixing is good enough.
Okay, thank you.
And or maybe just to put it this way, basically relational observables, what they are is they're gauge invariant extensions of gauge fixed quantities. But then that just means, on my gauge orbits, I can evaluate, or basically I look at some gauge fixed quantity somewhere on that gauge orbit. And then I just extend it in a suitable way across the whole gauge orbit, such that the observable takes the same value everywhere along that orbit, but the value it takes is the same that the original observable took in a particular gauge. So in that sense, the numbers will just agree.
Okay, everything now has sense for me. Thank you very much.
Yeah.
Are there more questions for our speakers? So maybe I try to speak to you, Philip, again, because you mentioned that you motivated your framework also to say that you wanted to build phenomenologically interesting observables. Do you have something in mind for that?
Well, yeah, I guess any observables that could be tested in experiments. I mean, I guess even one could ask these questions perturbatively. for instance, one could even ask formulating the phenomenologically very relevant observables that Michael talked about. In principle, you could also discuss those in a gauge invariant context. Though in that setting, since it's perturbative, you would have to basically restrict this gauge invariant approach to a perturbative setting, but which in principle is possible. But of course, for us, there was more the motivation of having at least a general framework that can handle, at least in principle, whatever a gauge invariant observable is. So we had a somewhat broader question to start with. But then once you have such a framework, then you can ask, of course, more specific questions about particular solutions or so, where you might want to, consider what sort of concrete observables we might want to write down, which would be examples of the type of what I presented.
A question actually to both speakers, both Philip and Michael. If we pretend that scattering amplitudes are non-perturbative, or whatever way we calculate them, would you do comment how they can fit into approach of again, gauge invariant or relational? Because implicitly when we scatter some, we have in, we have out, we assume some reference frame and certain choices. So it's a bit like invariant observables where we fix things on the boundary. Can you comment more on potential relations?
Do you want to go first? Or
I mean, from my side, I can only say that if you had a fully non-perturbative scattering amplitude, it has, of course, more properties, maybe, like there's additional information in there, but it like in for example, this observable-based framework, you just put it in and you get the non-perturbative observable out from that. And then I'm not sure, yeah. So, yeah.
Yeah, I mean, these observables, they will fit, I mean, like scattering matrices and so on, they will fit into this relational observable program, but I would think of it more in a perturbative setting,
Okay.
Yeah, but
in theory, it's easy. In practice,
yeah, in practice, okay. How you do that in practice, I haven't thought too much about it. But there exists a paper by Don Merrill that kind of touches a little bit on that, but in a very preliminary way. So it's I would say overall an open problem how to really relate relational observables and scattering amplitudes, scattering matrix.
More questions from the audience to one of our speakers. So, Michael, something that I was wondering about is there a connection also to effective field theories, like where you would try to treat gravity as like a perturbative quantum field theory, and you're looking at the low energy quantum corrections?
I mean, this was on one of my slides. This is the basic setup that we're using. We never go beyond the leading order in principle, but you could include the higher order, the higher derivative operators.
Yeah, that's what I meant. Like, do you include R squared and such terms?
So we in our works, we usually were concerned with the classical part of the computation, but people have studied this, like for example, contributions of these higher derivative operators to certain observables like time delay and so on. There's this in the literature, yeah.
Renata? Just wait one.
That's a question to Philip. I wanted to ask you if you have an intuition about which of the three different setup to construct relational observables is more fitting in order to make contact with cosmological observations.
Well, I would say since they're equivalent, it doesn't matter. But
That's fair.
But you can ask the question of which one is maybe the most convenient one to use overall, and I find the covariant one the most convenient. And that's just the simplest way of I mean, once you have such a reference frame, the simplest way in which you can dress general tensor fields, and in fact you can even, I didn't discuss that, observables or kinematic observables that are not gauge covariant, so you can even generalize it beyond that. So yeah, it's just much simpler in that setting than, for instance, in the single integral approach, or in the power series construction. Talking about tensors is actually a little bit complicated.
Then I have a follow-up question. If you try to make contact with cosmological perturbations, then I have a conceptual, like a bit of a confusion if then the perturbations are defined on your reference fields, on your background structure or coordinate structure. Is there some ambiguity, or there is some preferred way to do that?
Well, there is, of course, an ambiguity in the sense of which frame do you choose, and although you're going to be gauge invariant, you're going to be frame dependent. And so, but the thing is that this convention of which frame you choose isn't actually a gauge fixing in the usual sense. So these frame change maps that I actually didn't have time to talk about, they're not gauge transformations of the theory in the sense of, so in contrast to coordinate changes, fixed coordinate changes, which map to gauge directions on the field space, which lead to degenerate directions of your pre-symplectic structure, these ones don't. So you can think of these physical frame changes basically in the same sense as in special relativity or special relativistic field theories, where it's, changing Lorentz frame is a change of convention, but it's not a gauge transformation. It doesn't amount to degenerate directions on field space that you factor out. So you can think about it in the same way as so in some sense, once you deparameterize your series using dynamical frames, you're kind of special relativizing general relativity in some sense.
I had another question for Michael. So you touched about this on very briefly, that you are, at the moment, you're really only computing like scattering angles, or, I mean, not non-bound systems essentially, which is of course not what you would ideally like to. And you mentioned that there's, well, okay, maybe you can expand, I don't know, because I don't know, how do you go from essentially the potential that you would get, for example, for the scattering event to the potential that would be relevant to compute waveforms or in spiral or bound states, let's say, in the end. Right. So what exactly is involved there, or is this, to what extent is this solved?
I'm not sure how familiar you are with the status of these things. So this is, of course, a very complicated problem at some point. Up to the previous order, it's, or like to the order G to the 3, it's possible to the instantaneous potential is a well-defined object, so you can just transport that to from between the, I mean, it's the same potential. The Hamiltonian is universal. But once you go to the 3-loop order, you'll find that the instantaneous potential by itself is not well defined. It's divergent. So you have to compute a more inclusive quantity, also including radiation modes. But that thing then is not universal. It depends on the structure of the object you're considering. So, and in particular, there's this story with the memory effect that's very closely tied with that. So, so for that things, I think still the understanding hasn't improved too much in the past few years. But yeah.
More questions? So maybe a question for Christoph. So I was wondering, can you compare your, I mean, you mentioned the scalar field in the beginning, and people previously defined, for example, D'Alembert operators on causal sets. Is there a relation to those previous attempts, or can you generalize also these constructions, I mean, these very formal algebraic constructions to more general metafields?
Yeah, so as I've shown in the end, I mean, the state what we construct, that is a state that is kind of already known in causal set theory. So this is essentially just a more mathematical way to construct the same state without necessarily using the axioms. So they are implicitly in there. But the way you discretize your fields does not really matter too much. I mean, this gives you then different operators maybe, so the different relations for the symplectic form. But I think this would be just amounting to some changed constants, at least in this finite dimensional setting.
So that you have a few ambiguities in the procedure in principle, but the qualitatively it's not too different.
Christoph, I have a very elementary question. Early on, you mentioned that embedding of this causal set is possible in 1+3 or higher dimensions. So, what technically goes wrong if you try to do it with 1+1, for example?
Well, you can try. So the dimension. So I've said that this would only embed in so if you take Minkowski spacetime. So if you really want to embed it in flat spacetime, then it depends how many dimensions you have. So well, as a subset of one of these graphics, you have this sort of crown, for example. So the crown is one that needs 2+1 dimensions. And I mean, you can just try to draw it. So if you want to embed this in 1+1 dimensions, well, then you would need to have another link between the two central elements. And because you don't have this link, you can't do this. And you can actually try to visualize what is actually corresponds to. This essentially corresponds to two triangles if you try to draw them symmetrically. So one in the first time slice and in the next time slice. And that's why you have all the simplex there.
Okay, so I have a question for Christoph as well. So in these discrete approaches, when you couple matter, there is the very often question about how to couple chiral fermions in this type of theories. And as far as I know, in the loop quantum gravity community, there is a debate about if there is the doubling problem or not. And in your case, I mean, you just said that in principle, you can discretize the metafield and couple to. Is there any idea about how to couple chiral fermions in a causal set scenario?
Well, as far as I know, there is not very much done on this topic. But I must admit, I also don't know about the details of those things that have been published before. But this is definitely an interesting question on how to encode fermionic fields on causal sets, or even with some properties of the causal set. So to connect this more to a quantum structure in the spacetime itself, because otherwise causal sets are rather like a discrete model of spacetime. So they are not, in that sense, not quantum spacetime yet. So they're just discrete gravity.
Yeah, I think the problem with chiral fermions is that it's already at the level of the discretization. So it's
yeah. So there would probably be an influence directly between the causal structure then that you have to this.
Thanks.
Yeah, maybe I need to extend on this question, Antonio. In loop quantum gravity last year, there was a paper by Mushin Han and other people where they showed that this fermion doubling part was exponentially suppressed, and I think this was mostly because they looked at superpositions of different space discretizations.
Yeah, so it comes from the fact that space-time is dynamic. You have to consider that it's quantum space-time.
Okay. More questions. You can also raise your own points that you always wanted to ask these experts on observables. Also, the speakers can ask each other questions if they want to.
Maybe I have a question. So, do you think so? What would be the most experimentally falsifiable observable that you could think, where you could also say, well, maybe that sort of theory of quantum gravity is favored over another. Is there something like that?
So you're asking about quantum observables now? Yeah. Is there one observable that clearly favors one over whatever the outcome, that favors one approach over another? That's hard because one, first of all, has to come up with observables that have a meaning in different quantum gravity approaches. And so, you have to be able to somehow promote some of these observables into the quantum theory via whatever quantization technique, which will depend very heavily on whatever your approach is. Or maybe you may even want to compare genuine quantum observables that are not even classically definable in this way. But yeah, I'm personally not so aware of any good candidate that would be, common to many approaches that would be viable for phenomenological purposes. I mean, there's of course certain observables such as spectral dimension or so that are studied in many different approaches to quantum gravity, but I don't know how phenomenologically accessible something like that is. So I guess you're asking about something that would be phenomenologically accessible. And I mean, presumably the observable should have some connection to classical observables just because our universe appears very classical on large scales. But yeah, I mean, I in one way or another, probably cosmology is maybe your best playing ground, and then for that it would be sufficient to look at perturbative observables and maybe relating it to the CMB. That's something that, I mean, in principle, of course, all approaches to quantum gravity should somehow relate to.
Yeah, on that note, actually, I think you can look at quasi-normal modes in the decay of merging events. And then with Lisa, we will be able to detect them eventually. And depending on your cosmology, you can assume that you will have this black hole echo effect. I don't know if you heard of that, which tells you basically that the quasi-normal modes will be reflected by the horizon of the black hole, and we will at some later time pick them up. And what frequency these quasi-normal modes will be, what frequency we will actually measure, that heavily depends on the theory of quantum gravity. So for instance, in loop quantum gravity, you will have like a phenomenological constant which enters this frequency, like this discrete frequency spectrum, and in string theory you might have some smooth behavior, like some smooth decay of reflectivity of depending on the frequency of the wave. So I think this will be, well, not soon, but in 10 years, hopefully, when Lisa will start, this will be a real chance to see that actually.
Yeah, I agree. I mean, I guess black hole observables are, in particular, that are detectable by gravitational wave detectors is another good playing ground, yes. Great.
So, Philip, just a question regarding, well, let's say notation. So when you say observables, you mean simply gauge invariant objects?
Yes.
Or you mean something that you can go to the lab and measure?
Yeah, so I would call that a question of terminology, not notation, but
okay, yeah.
no, but yeah, you're right. I mean, the observable is understood in the sense of, in the crude sense of just gauge invariant objects that could, in principle, that have physical meaning in the theory, but of course, whether they are then actually observable in experiment is a wholly different question. And in some sense, calling those observables is indeed a bit of a misnomer. There are other suggestions, I think, going back to John Bell or something, like calling them beables or something like this. That's.
Can you speak louder?
Oh, was that not okay? I don't know what you didn't understand, but
the part, the Bell part, yeah.
Yeah. So I mean, there were proposals for calling what I called observables, something else like beables or something like this, and just to distinguish them from things that are actually observable in experiment, and probably is a good, it makes sense to distinguish them. But here I was really just taking the standard terminology of the field of, you know, quantum gravity that's kind of a bit remote from actual experiments, and then people just call things observables that may not be.
I'm just saying that because there is a counter, well, let me put like that, there is a potential counter example in Yang-Mills theories where you dress your gauge field and you compute, for instance, the 2-point function for these dressed fields.
Yeah.
And it violates, for instance, reflection positivity.
Okay.
So that would be, I mean, that's a terrible property. I mean, and it's a gauge invariant correlation function.
Yeah, I mean, I guess it's not just a question about gravity data. I think it's true in, as you say, in gauge theories more generally. No, but I think, it's a fair point that one should distinguish this. But it's just, I think, very difficult, given the formalism of gauge invariant observables, you know, to actually determine which ones of them are observables.
Thanks. Well, just as a former quantum fundamentalist, I would just make a pedantic comment that, as you said, your talk was classical. So the name refers to the hope that those gauge invariant entities will be in some form quantized, and the classical part is not easy, and there is of course no guarantee that their quantum counterparts will not have some additional horrible properties. We just hope that this is not going to happen.
Yeah, point taken.
Okay, we have a little bit less than 10 minutes left. Anyone else? Maybe someone wants to be provocational?
Renata wants to be provocative.
No, actually, it's a very naive question to Michael. From the scattering amplitude, then usually what we do in QFT, then we construct like the cross-section by integrating over angular variables and so on. And also for gravitational scattering amplitudes, you use the same flat methods or like straight space-time methods, or you take into account the fact that the background can be also curved and
So in all what I was discussing, it was assumed that it would be flat, but people have considered scattering in backgrounds like shockwave backgrounds, or I mean, an interesting background is of course like computing a 2-point function in a background of another black hole. This kind of thing is interesting. Yeah.
Another non-provocative question to Michael, maybe. So when you're saying that you calculate the gravitational wave memory, or you link your calculations to the memory effect, is it then via the infrared triangle relation that you just have the soft theorems, which are basically more or less Fourier transformed version of the memory effect, or what are you referring to?
Yeah, that's pretty much how it works in practice. This is not a computation I did myself. This is work of other people.
Yeah, I'm just asking. Yeah. Okay, thanks.
So does anyone else have a question or a contribution to this discussion? Well, if that is not the case, maybe we close a little bit early, but before we all leave, let us first thank the technical staff for making this possible and also letting the people online share it, and thanks again to all our 3 speakers for this afternoon session.